Hey guys, welcome back to Step by Step Academy. Our topic for today is number-based system from the West African Examination Council Mathematics Curriculum. Our focus today will be on the concept of number-based system and conversion from any given base to base 10. We'll begin right away with the concept of number-based system. For instance, the base 2 number system uses only 2 digits to represent any of its numbers, and those digits are 0 and 1. A base 10 number system uses 10 digits to represent any of its numbers, and those digits include 0, 1, 2, 3, 4, 5, 6, up to 9. From the table below, we have several number-based systems beginning from base 2 down to base 10, and the number of digits used by each of these number-based systems. As said earlier, the base 2 number system, which is known as binary, uses only 2 digits, zeros and 1. The base 3 number system uses only 3 digits, 0, 1 and 2. The base 4 number system uses only 4 digits, that's 0, 1, 2, 3. The trend continues like that up to whatever number base you have. The implication of this is that for a number in base 2, a number in base 2 can never have any other digit other than zeros and 1. Take for instance, suppose I want to write 2, base 10 in base 2, that will be 1 and 0, base 2. Similarly, 3 base 10 in base 2 will be 1 and 1, base 2. 4 in base 10 will be 1, 0, 0, base 2. Similarly, suppose I want to write 3 base 10 in base 3, that will be 1, 0, base 3. 4 base 10 in base 3, that will be 1, 1, base 3. 5 base 10 in base 3, that will be 1, 2, base 3. Now, if we take a close look at all the digits that make up this base 2 number, we'll see that whatever number it is we're writing in base 2 is just a combination of zeros and 1. Similarly, if you look at the numbers we have here in base 3, we also see that it's just combination of 0, 1, 2. What this implies is that a base 2 number will use only 2 digits to represent any of its numbers, while a base 3 number will use 3 digits to represent any of its numbers. No matter how big the number it is, as long as the number is to be written in base 3, the digits that make up the number must be combination of 0, 1 and 2. Also, from this table, another interesting thing to note from the table is that we notice that the digits that make up the digit that is used by a particular number-based system, they are each less than the base. For instance, the digits used by the base 2 number system are zeros and 1, which are each less than the base. The digits used by the base 3 number system, they are 0, 1 and 2, and they are each less than the base. This implies that the highest digit for a base 2 number system is 1. The highest digit for a base 2 number system is 2. Base 3 rather number system is 2. The highest digit for a base 4 number system is 3, and on like that. The implication of this is that it would be wrong to have this type of number in base 2. Why? Because 2 cannot be part of the digits that make a base 2 number. Also, 2 as a digit cannot be equal to the base. Similarly, it would be wrong to have 131 base 2. Why? Because 3 cannot be part of the digits that make a base 2 number. A very good example of base 2 number will be 1001 base 2. If we look at the formation of these, we'll see that the digits that make up this number, they are zeros and 1, and they are each less than the base. This fact is true for every other number-based system. Apart from the number-based system listed on this table, there are several other number-based systems that are worth mentioning. We have the undecimal number-based system, which is base 11. We have the duodecimal number-based system, base 12. Hexadecimal number-based system, base 16. Vigesimal number-based system, base 20. Sexagesimal number-based system, base 60. This undecimal number-based system uses 11 digits, beginning from 0 up to 10. But here, 10 is represented with letter A. The duodecimal number-based system uses 12 digits, and those digits includes 0, 1, 2 up to 11. And here, letter B represents 11. In the hexadecimal number-based system, it uses 16 digits from 0 up to 15, and letter F here represents 15. The vigesimal number-based system uses 20 digits, that's beginning from 0 up to 19. K here represents 19. Please note here that for the vigesimal number-based system, after letter H, we're meant to have letter I, but the letter I here has been replaced with letter J. The reason for this is because letter I is considered to be similar to the digit I, to the digit 1 rather. So in order to avoid confusion, letter J is used in place of letter I. And letter J here means 18, letter K here means 19. If you count numerically beginning from 0. The sexagesimal number-based system uses 60 digits beginning from 0 up to 59. And the sexagesimal number-based system works like the clock. Of all these number-based systems, the common number-based systems in use today are the binary number system, which is base 2, the octal number system, which is base 8, the denary or decimal number system, which is base 10, and the hexadecimal number-based system, which is base 16. Having understood the concept of number-based system, we now move over to conversion from any base to base 10. A number in base 10, e.g. 3264 base 10, can be written as 3000 plus 200 plus 60 plus 4. Why is this so? The reason is because the place value of 3 in this number is 1000. The place value of 2 is 100. The place value of 6 is 10, and the place value of 4 is a unit. This number can be written as 3 times 1000 plus 2 times 100 plus 6 times 10 plus 4 times 1. Now, if we write these multiples of 10 in index form, we will have 3 times 10 to the power of 3 plus 2 times 10 to the power of 2 plus 6 times 10 to the power of 1 plus 4 times 10 to the power of 0. A quick reminder from the laws of indices, an index with a power of 0 will always be equal to 1. So this 1 in index form can be written as 10 to the power of 0. Now, if we look at this long expression, if we compare this long expression with the value 3264 base 10, we notice straight away that the 10 attached to this 4 has a power of 0. That means there's a 0 on top of the 10. The 10 attached to this 6 has a power of 1. So we put 1 here. The 10 attached to this 2 has a power of 2. So we put 2 here. The 10 attached to this 3 has a power of 3. So we put 3 here. So this means that to move from the right to the left, we can do each digit multiplied by the base raised to power whatever number or digit is assigned to whatever power is assigned to that digit. I take that again. To move from the right to the left, that is from the right hand side, if I want to have this same expression on the left hand side, we use each digit that make up the number to multiply the base raised to the power the digit assigned, the power assigned to the digit. I take that again. The digit 3 multiplies the base 10 raised to the power, the assigned power to the digit. The same thing, the digit 2 multiplies the 10 raised to the power assigned to the digit 2. The same thing for 6, digit 6 multiplies the base raised to the power assigned to the digit. If we apply this same concept to another number in another base, let's say for instance 11101 base 2, and I'm required to convert this to base 10. I begin first by assigning powers of 0 starting from the right towards the left. I assign powers of 0 starting from the right towards the left. 0, 1, 2, 3, 4. The next thing now will be to use each digit multiplies the base raised to the power assigned to the digit. So this will be 1 times 2 to the power of 4 plus 1 times 2 to the power of 3. The next digit is 1 times the base raised to the power assigned to the digit. That will be plus 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 plus 1 times 2 to the power of 0. Whenever a number is taken through this process, the number is said to have been converted to base 10. So this is the process a number goes through when it is required for the number to be converted to base 10. If we simplify this further, 2 to the power of 4 is the same as 2 times 2 times 2 times 2, and that will give us 16. So this will be 1 times 16. Similarly, 2 to the power of 3 is 2 times 2 times 2, and that will give us 8. Also, 2 to the power of 2, that is 2 times 2, and that will give us 4. 2 to the power of 1, that will give us 2 plus 1 times 2 to the power of 0 will give us 1. If we simplify further, we'll have 1 times 16, that will be 16. 1 times 8, that will be 8. 1 times 4, that will be 4. 0 times 2, that will be 0. And 1 times 1, that will give us 1. And finally, if we add up all these numbers together, 16 plus 8 will give us 24. 24 plus 4 will give us 28. 28 plus 0 will give us 28. 28 plus 1 will give us 29 base 10. Therefore, 11101 base 2 is equivalent to 29 base 10. This is how we convert a number in any given base to base 2. For emphasis sake, we'll look at more examples on how to convert from any given base to base 10. Remember again, the procedure is to first begin by assigning positive power beginning from the right towards the left. So we start by assigning beginning from 0, 1, 2, 3, 4, 5. Now the next step will be to use each digit in this number to multiply the base raised to the power assigned to the digit. So this will be 1 times 2 to the power of 5. So we have 1 times 2 to the power of 5 plus 0 times 2 to the power of 4 plus the next digit 0 times 2 to the power of 3 plus 0 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 1 times 2 to the power of 0. The next thing now will be to simplify 2 to the power of 5 That means 2 times 2 times 2 times 2. That will give us 32. So we have 1 times 32 plus 0, that's the next one is 0, times 2 to the power of 4, that's 2 times 2 times 2 times 2, that will give us 16, plus the next one is 0 times 2 to the power of 3, that is 8, 0 times 2 to the power of 2, that will be 0 times 4, plus 2 to the power of 1, that's 2, 1. So the next one will be 1 times 2. And then lastly, for the last term, we have 2 to the power of 0. That will be 1 times 1. Remember again that any index with a power of 0 equals to 1. So from here, we now multiply 1 times 32 is 32. 0 times 16 is 0. 0 times 8 is 0. 0 times 4 is 0. 1 times 2 is 2. And then finally 1 times 1 is 1. And lastly, if we add up all of these together, 32 plus 2 plus 1, that will give us 35 base 10. In other words, 100011 base 2 is equivalent to 35 base 10. Apart from this method, there are other methods of converting a number in any base to base 10. So for example 2, I will use a different method, and I like to refer to that method as repeated multiplication and addition. Repeated multiplication and addition. So what the method is about is that we use each digit to multiply the base, then we add the next digit. Each digit multiplies the base, we add to the next digit. We multiply the base again, add to the next digit. We multiply the base again, add to the next digit until there are no digits left. Let's illustrate that with this example too. So the first digit here is 2. That will be 2 multiply the base, that's 3. Then we add the next digit. After 2, the next digit is 1. That's plus 1. 2 times 3 plus 1, that will give us 7. This 7 again will multiply the next digit, which is 2. That's 7 times 2 plus, we'll multiply the base, I beg your pardon. That will be 7 times 3. We'll multiply the base, 7 times 3 plus the next digit again, which is 2. 7 times 3 is 21. 21 plus 2 will give us 23. 23 again will multiply the base, add to the next digit. That will be 23 times the base plus the next digit. The next digit is 2. That will give us 23 times 3, that is 69. 69 plus 2 will give us 71 base 10. So this is a quicker method of converting a number in any base to base 10. Now for example 3, I will use the first method I used in example 1. We'll apply the same method in example 3. Remember, the first thing will be to assign positive powers starting from the right towards the left, beginning from 0. So we have 0, this is 1, this is 2, this is 3. The next step will be to use each digit, multiplies the base, raised to the power assigned to the digit. So this will be 1 times 16 to the power of 3 plus C. Remember, letter C is 12. In hexadecimal number base system, letter C is 12. So 12 times 16 raised to the power assigned to the C. 12 times 16 to the power of 2 plus letter A, which is 10. That's 10 times 16 to the power of 1 plus the last digit, which is 2 times 16 to the power of 0. Now we go ahead and simplify. You may need to bring out your calculator at this point. 16 to the power of 3, that means 16 times 16 times 16. And that will give us 1496. So we have 1 times 4096. The next term is 12 times 16 squared. 16 squared is 256. That will be 12 times 256. 16 to the power of 1 is just 16. So this will be 10 times 16 plus the last term, which is 2 times 16 to the power of 0. That will give you 1. If we simplify this further, 1 times 4096, that will be 4096 plus 12 times 256. 12 times 256, that should be 3072. 3072. Then 10 times 16, that will give you 160 plus 2 times 1, that is 2. Finally, we add up these values together and that should give us our final answer. So finally, if we add this plus this plus this plus this, we will have 7330 base 10. Why don't you go ahead now and try this number 1 and number 2 here. Here you have 342